So I want to continue examinations of integers. I want to look at integer representation of the algorithms that go with it. We went through the division algorithm in the recording from what would have been Monday. We went through modulus and quotient, remainder, all of those pieces. Those are important algorithms to how we represent integers. Stupid question of the day. What's that number? Say it again.
3,241.
So by default, we are working in piles of powers of 10, right? You said 3,000s, 200s, 4 10s, 4t, 1. But all of these are decreasing powers of 10. Why? You might think that's the greatest idea on the planet, right? I got 10s, I can do this in 10s. I have 12. Count the joints on your finger. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Why don't we use 12? Some people do. Different numeration systems exist for different cultures. There's a group in Mesoamerica, I don't remember which, whether it's Incan, Aztec, whatever, that counts by body parts up one arm and down the other. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh boy, I'm in trouble, right? But there's no well-defined reason for us to be forced to use 10. We use decimal by default. By the way, the words for our numbers are physical. In a lot of cases. Anybody taking German? Count 5. Count 5. Ein,
2, 3, 4, 5.
fünf. Thumb. Literally, 5 is to take the thumb. It's ingrained into what we do that we think in these behaviors. Gettysburg Address. Anybody know the start of the Gettysburg Address? What the hell's a score?
I think 20 years.
Why 20? A person's word. 5, 5, 5, 5. Anybody take French? 87 years, right? 4 in French. 4 20s and 7. French use score by default for higher numbers. Who made this crap up? We did. And what I've written here can be generalized in that fashion. Pick an integer bigger than 1. And then we're going to do it in general. Then for any other integer, I'm going to go ahead and just deal with positive integers at the moment. For any other positive integer, there's a unique way to write n in terms of the number b you've chosen. Just like at the top, I've written these things in powers of 10. I can write it in powers of b for any b you want. We're going to call this the base b expansion of n. By the way, k is just an index. Like 3 was the thousands place. It's our fourth position. Well, technically, k would be 3 because I have here a 0th position. And then the AI, a k minus 1, all the way down to a0, those are numbers. And they are forced to be between 0 and b. And the only restriction is the very first one, the leading one, AK, is not 0. So the number I wrote, 3241. I read that as 3,241 because I was thinking in base 10. Let's change the base. I've decided to write this number in base 8. And to quote Tom Lehrer, base 8 is just like base 10, if you're missing 2 fingers. Instead of powers of 10 that I had written at the top one, I'm going to do the exact same setup and just write powers of 8. This is 3 times 8 to the third, and 2 times 8 squared, and 4 times 8 to the first, and 1 times 8 to the 0. I just took the tens that we had in the original expansion, or decimal expansion, and replaced them with 8s. What's this number? Well, I could answer that question by saying, well, it's 3241 base 8, because that's a number. What is the decimal equivalent of this number? I need 8 to the third. 8 times 8 is 64. What's another 8 in there? So this is 3 times 512 plus 2 times 64 plus 4 times 8 plus 1 times 1. That's 1536 and 128 and 32 and 1. Somebody got this one before I've done? Who's added this up right?
1697.
Say again?
1697.
1697. Ta-da! You can use any base you want, and the decimal value of the number changes based on our choice of base. There's no reason to use any particular number over another. Base 12. Same question. What's the decimal equivalent of 3241 base 12? Please notice I can't read it 3000s anymore. I'm not dealing in thousands. I'm dealing in powers of 12, and 12 cubed is something weird. You got a total for me, Seth?
Yeah, 5,520.
I don't care what base you want. Could pick base 36. Could pick base 102. Doesn't matter. What's a base I can't pick for the number 3241?
0.
I can't pick a base of 0 ever. What about that number restricts my bases?
The exponents are always 0, like 0 to anything is 0 except for 0 to 0.
Right, but again, that applies regardless. There's something specific about 3241 that limits the number of bases, well, that restricts the number of bases I can use. There are several bases I'm not allowed to use here.
Anything bigger than 3241?
Then it would just be a one-digit number. Here's my definition of an expansion. The numbers I use must be smaller than the base. So I'm using 3 and 2 and 4 and 1. I can't do this in base 4. Can't do this in base 2. Can't do this in base 3. Because the digit 4 isn't permitted in base 4. The digit 2 isn't permitted in base 2. The digits we use must always be smaller than the base. So as soon as I see this number, I know the base has to be bigger than 4. Because there's a 4 in there. But if I had a number that consisted of only digits smaller than 4, I could do that in base 4, or any number bigger than 4 could be an appropriate base there. I forgot my parentheses. Wait a minute, that means if I'm writing a number in base 2, what are the only digits I'm allowed to use? 0 and 1. And in base 5, what I use base 8, right? I use base 8. In base 8, I only get 0, 1, 2, 3, 4, 5, 6, and 7. In base 12, I need digits for 0 through 11. Those need single symbols. So I should get a 0, a 1, a 2, a 3, 4, 5, 6, 7, 8, 9 deck L 10 and 11. Because when I write a dozen, 1 0 in base 12 is 1 times 12 to the first plus no ones. So you write a dozen as 1 0. Because I'm in base 12. Base 16. Same deal. I need individual single characters for 0 through 15. All UCS people, welcome to your blue screen of death stuff. What happens when your computer crashes in Windows? Blue screen of death pops up. What does it say? I'm the only person on the face of the planet who's read a blue screen. It gives an error code. That error code is a memory location and what happened there. And it's written in hex. Hexadecimal, 16ths. 12, duodecimal. 8, octal. And base 2, binary. The most common bases we use outside of 10 are 2, 8, 12, and 16. But that means when I look at that error code, I might see something that looks like this. Error occurred at memory spot 2A F3. Oh, where the hell is that? So I'll ask the same question. What is the decimal equivalent of 2A F3 in hex? We'll write it out exactly the same way we wrote these out. We just have to remember what the digits stand for. So this is going to be 2 times 16 cubed, and then A times 16 squared, and then F times 16 to the first, and then 3 times 16 to the 0. But I start counting, what's A? A is 10. F, 11, 12, 13, 14, 15. And there I have my powers of 16. Again, I'm glad I have a calculator. What's 16 cubed? So this is 2 times 4096 plus 10 times 16 squared plus 15 times 16 plus 3. 8192 plus 2560 plus 15 times 16 is going to be 250. No, that's, yes, 250. No, 240. I can do math, really. 240 and 3, which gives me presto. So I can get the decimal equivalent for any number in any base by writing out the expansion and doing the arithmetic in the base in question. The hard part is keeping track of the digits. Questions? Yes.
The base, well, once you hit 9, you add why don't you do A, B?
I stole alpha and beta from Schoolhouse Rock. I am an old person. On ABC on Saturday mornings, they would play cartoons. And back when the Federal Communications Commission came into existence, they said TV is a vast wasteland that will rot your brains. And so the department, Federal Communications Department said, you must put on educational TV program. And in between Saturday morning cartoons in the 70s and 80s, they ran 1-minute animated shorts on arithmetic, civics, science, and grammar. A noun is a person, place, or thing. The preamble to the Constitution. I can only do it if I sing it to the stupid song they did about Schoolhouse Rock. They did counting by 12s. Music video called Little 12 Toes. On our Canvas page is a link to that video, and they use 1 through 9, 0 through 9 and then alpha and beta instead of A and B. So I stole it from them.
So I,
You could absolutely use A and B. Again, as long as you tell me what those are. Questions? Keep talking. So if I give you a number in some weird base, you can turn it back into a normal number. How do I go the other way? One hundred and 11. If I don't put parentheses and a base number, it's assumed I am talking about a normal number in base 10. So 111. I want it in octal. I did it. There are dozens of different algorithms that will do this. I'm sure if you give yourself a minute searching, you can find some code that you can program somewhere. What's the code going to do? Now I go back to what was on Monday's video. And I talk about division. When you divide by 8, the 111 evenly divisible by 8. So there's a remainder. What do you know about that remainder?
What's the name?
And it must be non-negative. It's a number that is forced to be between 0 and 8. Just like our digits. As a matter of fact, what is 111 divided by 8? I actually want the quotient and the remainder. Something times 8 with something left over. I was about to say, that's definitely not right. Because 6 times 8 is 48. And
What's the?
so 13 times 8 with 7 left over, right? 13 groups of 8. Wait a minute, that's the same as saying that this is 13 times 8 to the first and 7 times 8 to the 0. That 7 is my ones digit. Problem, 13 is too big. 13 is bigger than 8. Divide again. How many 8s with what left over?
8 with 5 left over.
Now that would go here, right? That's already multiplied by an 8. So this 1 is actually multiplied by 8 twice. But what I really did is I slid this over and I said, oh, divide again. Let's slide it over and divide one more time. This last division always works the same. How many 8s do I have to make a 1? 0. As long as I have 0 8s, I know to stop. Lo and behold, these are the digits I want in my base 8 expansion, reading from bottom to top. 111 is 157 in octal. 1 8 squared, 5 individual 8s, and 7 1s. All I have to be able to do is the division algorithm. Give me a quotient and a remainder, and then iterate that process until I get a quotient of 0. This is a base change algorithm from any base you want. 117,130. The hex. My first quotient and remainder.
Seven, three, 20. 7,320, and 16 plus 10.
Which means that first digit, well, that first number, my ones, should be an A. Repeat the process. 7320 is something times 16 with something left over.
Uh, 457 times 16 plus 8.
And I'm going to keep going until the quotient I get is a 0. And then I read them from bottom to top. If I'm converting to binary, I'm just repeatedly dividing by 2 and seeing if my remainder is a 0 or a 1, which is a matter of looking whether the number's odd or even. So that's easy. Ta-da! It's an iterative behavior. And you stash the digits in order from right to left. Ta-da! This is, again, a greedy algorithm, page 263. Because it takes the largest piece first, the largest number of multiples of your base. Questions? Binary, octal, and hex all have the common behavior that they are all related. Because 8 is 2 cubed. And 16 is 2 to the 4th. So it turns out that it is really, really, really easy to switch between things that are in base 2 and 8 and 16. Actually, going via base 2 is the easiest version. Again, on page 263, just above that algorithm we were just looking at, is a table that shows the binary numbers from 0 to 15. And above that, the octal numbers from 0 to 15. And above that, the hex numbers from 0 to 15. And because of the grouping being that this is powers of 2, if I add leading zeros to these to make them all 4 binary digits long, wait a minute, binary digits, that's a bit where the word comes from. If I make these all 4-bit strings by adding leading zeros, then I can convert from hex to binary 1 number at a time. So that number right there, 1C98A, which is written out in base 16, can be turned into base 2 just by converting each of those hex digits to their binary equivalent. 1 is 0001. C is 12, right? On the table, 12. Turn to page 263. On the table, what's 12 in binary? Nine is 1001. 8 is 1000. A is 1010. So this in binary is equal to 1C98A in hex, which is the same as 117,130. But I didn't have to go back to base 10 to do it. As a matter of fact, converting from binary, octal, and hex to each other is absolutely trivial if you have that table. Or if you have the ability to count in binary on your hand. You seen this trick before? Ready? I'm going to count to 31. One hand. 1, 2, 1, 0. 3, 1, 1. 4 is rude. 5, 6, 7, 8, 9, 10, 11, 12, 13. I got them all. 12, 13, 14, 15. I can count 15 on these fingers alone. I don't need that table if I have this. But having that table sure as hell is a shortcut. I can convert from binary to hex or binary to octal by regrouping the bits. Here's a number in binary. I'd like it in hex and octal. Well, if I'm thinking in hex, hex is 16 is 2 to the 4th. So I'm going to break this up in groups of 4. And now I'm going to ask the same question. 0011, that's 3 in hex. 1001, 9 in hex. 1101. Say again? Because it's 13. That's C. What if I want to do it in octal? Wait, It's D. You said that and I wrote it down. What if I want to do it in octal? Well, that's base 8, and 8 is 2 cubed. So I break this same set of bits up, but instead of groups of 4, I do it in groups of 3. And notice I'm doing those from right to left. Because if I don't have an even number of bits, I'm going to have to add leading zeros on the left end. 0, 1, 1. Well, that's 3. 0, 1, 0. 1, 1, 0. One, 1, 0. Now, the other way to do it is to do it with the expansion. In base 8, I'm adding, base 8, base 2, I'm adding powers of 2, right? So these are 1s and 2s and 4s. So this is a 2. This is a 2 and a 1. This is a 4 and a 2. And no 1s. Your computer, your calculator, your smartphone, every single calculation device electronic calculation device on the face of the planet only computes in binary. I don't care what kind of computation you're doing. If you're doing addition or multiplication, you're doing those in binary. But the same algorithms we use still work in any base. I want to add. I know how to add. Hopefully you do too. I'm going to add straight down. 0 and 1 is 1. 0 and 0 is 0. 0 and 1 is 1. 1 and 0 is 1. 1 and 0 is 1. 1 and 0 is 1. What's 1 and 1? Oh, come on, people. That's not supposed to stump this room. It's 2, but there is no such thing as 2 in binary. So I have to write it in binary. What I have to do is I have to carry. But I'm carrying groups of 8, not groups of 10. Here, when I wrote down 1, 0, I said, oh, 1 and 1 is 2. Write down the remainder when you divide by 2, and then add the number of groups of 2. So here, 3 and 2 is 5. Oop, I forgot my little subscript. 4 and 7. Aha, that's 11. But 11 is an 8 with 3 left over. And now I get to carry that 1, and I get 4, 3, 5 basic. If I want to borrow, I have to borrow the same way. Remember this? You can't take 3 from 2. 2 is less than 3, so you look the 4 in the 10s place. Now that's really 4 10s. Make it 3 10s. Regroup. Change a 10 to 10 ones, and you add it to 2 and get 12. 12 take away 3 is 9. I didn't invent the snappy pattern. That's courtesy of Tom Lehrer. Right above the link to that little 12 Toes video on our Canvas page is Tom Lehrer's song New Math, where he does this problem live in a concert audience, playing piano at the same time. Can't take 7 from 3. 3 is less than 7, so you look at the 100th place. Borrow 100, add it to 3. 13 minus 7 is 6. 2 minus 1 is 1. Piece of cake. Same subtraction problem in base 8. Again, 3 is bigger than 2. I can't subtract, so I have to borrow. But I have to borrow from the 8th place. That's 8 to the first. And then I add to this 2. But I don't add 1, 10. I don't add 10. If I were to write this, that would be in base 8. But in base 10, what is that? 8 and 2, 10. 10 take away 3 is 7. And again, I do the same thing here. Can't take away 7 from 3, so I have to borrow 1, 3 is in base 8. But what's 1, 3 in base 8? It's 11. 11 minus 7 is 4. And 2 minus 1 is still 1. The best part is that the algorithms work the same way. The times table changes to all hell and back, but the algorithms work the same way. On the other hand, multiplying in binary is actually easier. Say that again. It's a bit shift. Multiplying by 2 simply takes everything and shifts it 1 bit to the left. Oh, wait a minute. Then if I did 101 base 2 times 1, I could really think of multiplying by 1, 0 and 1, right? Which would be copy down your number and shift it, and then copy down your number and then add. And multiplied by 3. No matter what binary number you're multiplying by, you really only need to know where the 1s are, and then shift and add. And that means multiplying in binary is much, much faster. It's big O of n, not big O of n squared. I find it easier not to write it horizontally. I find it easier to write these things vertically. So the first thing I do is I'm multiplying by 0. That's 0. The 3-bit number, I'll write down 3 zeros. But now I'm going to multiply by 1. Well, that's just a shift. Now I'm going to multiply by 1 again. That's another shift. So I shift over again. And then I just have to add. Unfortunately, no matter what I do, dividing, long division algorithm, sucks no matter what base you're doing it. There's no way around that. You'll have to borrow the next digit every time. Questions? The algorithm for addition, the algorithm for multiplication, the algorithms for computing div and mod appear on page 250, 265, 266, and 267. We're using these algorithms to do these numerical calculations. $64,000 question. Why? Why are these the right or preferred way to do these calculations? The algorithms in the textbook that are provided to you are actually the most efficient versions of these algorithms at this point. And then we can go through and determine algorithmic complexity. In any base, this is a single loop. In binary, it's nothing more than one loop, a condition check, and then shift it, and then sum them. That's 2 steps, n times. That's big O of n. Multiplying the long way is big O of n squared. That's a hell of a shift. But it gets even better. Because one of the things I want to do with nothing more than these ideas is encryption. As we talked about on Monday, you know, that's what pen testing is about, getting around, right? Well, if you have to, because encryptions are hard. It's much easier to physically walk into the building and take stuff. So how do I use these to do encryption?
You pick a random selection of numbers for this and you trade it with somebody else to handshake them. So you have a basically key and they have a key.
You skip way past a huge portion of the problem. What do you do with the key?
Shift it.
Straight shift? Straight shift's not secure. Ladies and gentlemen, I'll give you Julius Caesar. Anybody know the Caesar cipher?
Characters, right or left of it, no.
The Caesar cipher was just a shift by 3. That was what was used in the Roman Legion for the first thing. Then they realized, oh, hey, they just moved stuff over, we moved it back. That's not a secure cipher. So what are the basic secure ciphers? They're modulus. They're remainders. And that requires me to actually take the string of numbers I want to encrypt and raise it to a power and send you the remainder when I divide by your key. So what I need to do is I need to take a big string of numbers, I need to raise it to some power, and then I need to compute the modulus. Now, these are not small numbers. We're talking about numbers that are in binary, the bit length of your encryption key. 256-bit numbers. That's 10 to the 80th power. That's huge. How do I do that? Much less, that's only one character symbol. I have to do this with the whole message. I have to do it over and over and over again. That is what we will talk about on Monday, because on Friday, you're taking your exam. Immediately after our exam, I have a meeting over at St. Vincent at 2:30, so I got to hustle. We're going to be tight on time. So I will be here a little early. If you all wish to start early, we start up to 5 minutes early, but I need to have everybody in the room to do that. So y'all get here early, start early. I will see you all then. Please remember, you have another formula sheet you are entitled to use for this exam. If you came in late and still have homework to give me, please come give it to me. I will see you all on Friday.